All right, so here we are going on to part 5, which is talking about mass, weight, and the universal law of gravitation. There is a key difference between mass and weight. They are not the same thing, and that's what we're going to get into. I have a feeling this might go long, so let's get moving. All right, so what is the actual difference between weight and mass? All right, let's talk about mass. Mass is really just how much matter is present in an object. In other words, how much stuff is this object made out of? Okay, just how much stuff is there? How many atoms? How much matter is there? Okay, now here's a key point. The mass never, ever, 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 ever changes. The mass of this pen is the mass of this pen if I put it on Mars, it's the same mass. If I put it on the moon, it's the same mass. If I put it on the sun, well, it might completely burn up and turn into a whole bunch of stuff, vaporize. But if I keep all that vaporized stuff in a container, it would still be the same mass, okay? It's still the same stuff. If I put this out in outer space where there's no gravity, still, it's the same mass, okay? And it's measured in kilograms, so if I have something that's, I don't know, maybe half a kilogram, this is much less than half a kilogram, but half a kilogram, it's half a kilogram here, it's half a kilogram on the moon, it's half a kilogram on Jupiter, everywhere it's the same mass. Now, weight, on the other hand, is a measurement, but it's a measurement of the force due to gravity. And that's what I want you to kind of highlight here. It's the force. Weight is the force, whereas mass is the amount of matter. Okay? It's the force. Weight is the force due to gravity. Now, that force, the force that gravity pulls down on this, or the force in which gravity pulls down on this, what is that dependent upon? It's dependent on two things. Number one, it's dependent on the mass of the object. Objects that are more massive, I don't know. Okay, here we go. My coffee mug is more massive than my pen. This will have more weight because it has more mass than my pen. However, there's something else that it depends on, and that depends on how much gravity there is, or what is the acceleration due to gravity where you are. Okay? Right now, these both have the same amount of gravity because they're both on Earth. Okay? So gravity is pulling down on these with the same amount, if you will. Okay? Or these would accelerate at the same rate. If I drop them both at once, I'm not going to do that. But, okay, it's based on how much gravity there is. Now, if I put these both on the moon, still, this would weigh more than this. However, they would both weigh less than they do on Earth. However, I bet you if I put this out on, I don't know, let's say Pluto, where there's very little gravity, because it's a very small planet, this might even weigh less than this does on Earth. This on Pluto might weigh less than this does on Earth, because Pluto is very, very weak gravity. Okay? So it depends on the mass and how much gravity there is. So if I bring this pen to Mars, it will weigh less, but still have the same mass. Now the units for weight are newtons, and that's a key difference. Okay? Mass is measured in kilograms, weight is measured in newtons because it's a force. Remember, force is measured in newtons. Okay? All right, now we get to some equations here. Now, to calculate the weight of an object, you just take the mass of the object times the acceleration due to gravity. So W is weight, M is mass, and G is the acceleration due to gravity. Now, on Earth, if you were on Earth, that would be 9.8 meters per second squared, or really negative 9.8. This would be the mass of the object, and this would be the calculated weight, which you would then measure in newtons. Okay? Now you see, that kind of looks familiar, or at least similar to something else. And that's F equals ma, right? F is the force. Oh yeah, weight is a force. Mass, well, that's the exact same thing. And then acceleration. You're just using the acceleration due to gravity. So it's the same equation. It's just that this deals with the weight of an object based on the acceleration due to gravity on the planet. And this just has to do with, well, objects in general. Okay? So what you can also say, and by the way, these are really good to put in your essential equation sheet. Okay? What you want to do here, okay, or what you see here is that the force of gravity equals the mass times the acceleration due to gravity. These are all the same equation, basically. All you're doing is saying that weight is the force due to gravity. And you calculate it by taking the mass times the acceleration due to gravity, which is, on Earth at least, 9.8. Does that make sense? See, if I were to change it, let's say I go to Mars, it would probably be something closer to negative, I think it's 8 meters per second. Okay? So then the weight of the objects would be less, because this number here would be less. Okay? All right. So, where does the weight actually come from, though? Well, it's kind of weird. It's actually kind of interesting. It might blow your mind. Think about it. This thing moves. It accelerates, even though nothing is touching it. Nothing is touching it. And it falls down. That's actually quite mind-boggling if you think about it, because whenever you have something else, you have to push it to move it. Something has to touch it. But gravity is one of those sort of invisible forces. Now, I don't like to make it sound all weird, but it's kind of interesting how you don't need to actually be touching something in order to move it, but if you're using gravity. Okay? Now, Newton's universal law of gravitation. This was in the Principia. Okay? What he says is that anything and everything is attracted to, actually physically attracted to, anything and everything else in the universe. Okay? That's kind of weird. I don't see my pen moving toward my coffee cup, but here's the idea. If it has mass, like my pen does, it's attracted to, and attracts, everything else that has mass. So yeah, they actually are somewhat attracted to each other. Now you won't see this because these are such low masses. Okay? The other way of looking at this is that the force of gravity between two objects, okay, is directly proportional to the masses of the objects and inversely proportional to the square of the distance between them. So, if we put that into an equation form, we start talking about, okay, the force of gravity, that's what we're looking at, okay? That's right here. So, the force of gravity between two objects is directly proportional to the masses, right? So the masses are up top, directly proportional. So if you double the mass, you double the gravity. And it's inversely proportional to the square of the distance between them. That's the distance squared down here. It's inversely proportional. So if you double the distance, you actually divide by 4 the force of gravity. But if mass gets bigger, the gravity gets bigger. But if the distance between them gets bigger, the force of gravity gets smaller. So to put that into more physicsy, lazy, efficient terms, what we get is that the force of gravity right here, this is another essential equation, write it down, is equal to G, which is actually just a constant, okay? Just write that down on the side, okay? That G is just a constant. Okay, we'll give that to you in class. But that's not important here. The important part is a concept. Is that you take one mass times the other and you divide it by the square of the distance between them. That's R. R usually stands for radius, but it's the distance between them. Okay? So what you wind up getting is the force of gravity is whatever this number is times the mass of the pen times the mass of the coffee mug divided by the distance between them squared. Write that down. Now let me try explaining this in a slightly different way. Okay? It comes from gravity, right? It's the attractive force between two objects. Let's say the sun and the planets. The planets are attracted to the sun, right? So they actually are in orbit around it. They're attracted to it. Or maybe it's the moon and the earth. The moon revolves around the earth. Or maybe it's you and the ground. You are attracted to the ground, right? And it's even you and the person that you're sitting next to, okay? Now, I know it's kind of weird, but you guys are very, very not massive, so you're not going to actually see the culmination of gravity. You're not going to actually move toward each other. Okay? So then the question becomes, how does gravity actually make things move? Well, here we go. Okay? it attracts two things together. Let's say you've got two spheres, okay, two baseballs or something here, okay? Now, there are forces, okay, oops, there are forces that actually pull them together, okay? That's the force of gravity. Gravity pulls them together. Now, if you move them closer to each other, that force is going to be bigger. Now, I know that these force arrows are thicker. I'm sorry, they really should be longer, but then they start intersecting and it gets confusing, okay? Also, okay, you could increase those forces if you make one of the masses bigger. Notice now that the one mass is bigger than the other, so the force of gravity between them gets even bigger. Now again, if you're just doing softballs and baseballs, you're not going to actually see them move toward each other. But if we start making them bigger, if we start making one of those objects bigger and bigger and bigger and bigger, the gravity gets bigger and bigger. The force between the two gets bigger and bigger. But still, even if you do a bowling ball and a ping pong ball, you're not going to see it. It's not going to happen. You need to make it worlds bigger. Hint, hint. Okay? If we make it worlds bigger, like let's say let's make the other object the Earth, then you get the super big force of gravity like that. The force of gravity that pulls things down and accelerates them. Okay? Just imagine you started off with a baseball and a softball. They didn't really move toward each other. Make the softball as big and as massive as the Earth, and then the softball will actually start moving toward the Earth. Okay? And that's gravity. Gravity is what pulls the planets toward the sun. It's what pulls the moon toward the Earth, and it pulls you toward the ground. And that's it. That's it. If you have any questions about that, feel free to ask during class, and I'll see you then.